Alright, let's take a look at a different type of optimizer that we call momentum. Remember that if a function is non-convex, you can have local minima, or the surface can be relatively flat, and your gradient descent algorithm could stop there. Yeah? This is of course not what we want. So how does momentum work, and it has an analogy with inertia, with physics, is that you take a ball and you roll the ball down this, you just release the ball down to this half pipe. Yeah? Intuitively, you want to discourage, this type of movement, lateral movement, because this slows you down. And you want to encourage this type of movement along with the pipe. You want to encourage because this will make you speed up and converge faster. Yeah. So it's typically like this. You take a ball, you release it, and intuitively you can feel that as the ball gains momentum and speed, it's able to conquer these local minima, and eventually it will get here. Yeah. One issue with momentum is that, sometimes, so you have the ball here, and then you get an overshoot. Yeah? That's an issue. Not that it will not stick in this minimum, but it will take more time to come back to the minimum. Yeah? And there is a method for that, which we will see later. It's called Nesterov method. Just the intuition on the formula, so you have two effects. You have a significant effect of the momentum coefficient, because beta is 0.9, and this will drive the ball in the direction of the past. Yeah? Whereas this is your traditional term, and this will move the ball according to the current gradient. Yeah? So, and this alpha is still the learning rate, so that's what momentum is. Alright, let us now take a look at Nesterov, which is a variant of momentum, but it makes a lot of sense. So basically you do your gradient descent, your update rule, you go from W0 to W1, W2 you take a bigger step up because of the momentum, and at a certain point you're close to the minimum. Yeah? And this point would be your W3. So if you take the momentum formula, W3 is W2 minus beta update 2, right? So that's the historical effect. And then minus alpha gradient in W2. But the gradient in W2 is negative, yeah? So the gradient of C in W2 is negative, because the slope is like this. So you're gonna take this step anyway to the right, yeah? But instead of taking this term here, you want to take the gradient in the look ahead point. W3 is what we call W look ahead. And you can see that here the gradient changes sign, and so instead of adding another factor in this direction, you actually move back to this direction. And that's how you, of course, limit this overshoot. So the key is that that this W2, you change it by W look ahead. Yeah. There's no reason for you to take the gradient in 2, because the gradient will be negative, moving you even further. Yeah? So this is actually what Nesterov adds in terms of value. Okay, now we've seen all these optimizers, and you understand the logic. So one method is to make sure your alpha decays as we go along in the algorithm. Another option is to use momentum to survive the local minima. Alright, let us now take a look at Anna. probably the most popular optimizer at this point. And basically it is a combination of RMS prop plus momentum. Yeah. Momentum, RMS prop takes care of the alpha decay. Yeah, as we see. The learning rate will become smaller when we get closer to the minimum. And the momentum takes care of the overcoming local minima. Yeah. So very popular. This one, as well as RMS prop Atom, we're gonna see quite often.